So again, this is where we left off with last week, for those of you who were here. All right. Can someone give an example of a element that has a Latin name?
Letter what? Cadmium.
Which one?
Cadmium. Gold.
Cadmium, no. Gold is one.
Sodium.
Sodium is another. Potassium.
Aluminium.
Lead. Tin.
Aluminium.
Iron.
Silver. Potassium.
Okay?
Actinium. What is this?
All right.
Magnesium.
So when you look at your table there, you're going to see, I don't know, I want to say maybe maybe five important aspects in an element box. So just pick a number between 1 and 30.
27.
27. So if it's 27, is that cobalt?
Yes.
Okay. So when we look at 27, that's how we're going to refer to an element. So when we say 27, that is the atomic number. Any atomic number gives you the specific numbers of protons of that element. It identifies it, probably more so than just the name. So when we say element 27, these are arranged in increasing atomic numbers, 1 all the way to, I don't know, 119 maybe, 118, okay? So that's how you read these. They increase going left to right, but also going down as well. So when we're looking at 27, that is right here. It has a 27 in the upper left-hand corner of that box. So what else do you see inside that box besides 27?
CO.
Okay, so CO is the abbreviation for cobalt. What else do you see in there? Okay, so for me, I got to put these on because it's small. I can't read it. So we see +3, +2, 27, CO for cobalt, the word cobalt, and then 58.93 is the atomic mass for cobalt. Okay, so we haven't gotten that far yet. Those are what we call oxidation states or charges. Because when you combine them with other elements, that means these charges must add up to 0.
How do you add them up?
We haven't learned that yet. Okay. So as we move forward then.
Why is 57 to 71 and 89 to 103 all separate from the
Because
rest?
they're on the bottom.
Okay.
Wait, isn't one
I'll explain that in just a moment. Okay. So any type of atom, okay? Every atom on that periodic table has a specific number of protons. They can have the same number of electrons, and they may have similar numbers of neutrons, but every different atom is for sure going to have a different atomic number or that of protons. So when we look at this, okay, when we talked about table salt, that was what two elements from last week? That's one.
Sulfur.
And sodium. Okay? It's when you look at potassium and chlorine, that's a salt. Okay? And we could say lithium and chlorine, that is a salt. Rubidium and chlorine, that is a salt. You beat someone up, that is a salt. We told a funny. Okay? So what we mean by this, okay, we briefly talked about this, okay? This is highly, highly poisonous, chlorine, in its pure form. That's mustard gas, okay? It's toxic to the skin, okay? Sodium, I'll put that in a triangle, is highly volatile or explosive. Okay? When you put the two together, they stabilize themselves. Okay? And what we see happening is the smallest piece of matter that still retains the property of that element. So what we mean by that is the properties of this, which is stable, is totally different when they get broke apart. That's why I got arrows going in each direction. Okay? So the properties of... Can we continue? Can we continue? This means yes. Okay? So what we're trying to illustrate here is that the atoms of this compound are totally different than that of the compound itself. What makes up the compound, those properties are different than the element on its own. That's why we say sodium chloride is salt that we need in our diet. Depends how much. I really don't know how we'd want to answer that. But like we said, chlorine is poisonous. Sodium is toxic or explosive. And just so someone had asked the question about the, I think it was over here, about the charges, okay? They must add up to 0. Because if you look in box number 11, what does it say? Plus what? What does it say in box 17?
-1.
-1. So do those add up to 0 now?
Yeah.
Yes, they do. So that's what we mean when compounds form, the charges must add up to 0.
So if they have 2, then what happens?
Okay, good question. Like we said, different types of salts. You can also have this here, calcium chloride. Okay, element 17, that's still chlorine, that's got a -1. Calcium is element number 20, so what do you see inside 20's box? Plus what? Okay, so those charges also do not add up to 0.
What is UN?
We're not worried about that. Okay, so what is the least, not least common factor? That would be 1. But the least common multiple is what? If it's not 1, it must be what?
0.
No, you can't divide by 0. It's actually 2, the least common multiple. Okay? Now, this is not a value. Okay? It's just telling you that it's a charge. So when we do the math, if you know it's not a value, it's the charge. Don't think of it as 2 divided by 1 gives you -2. Okay? It just gives you 2. So what is 2 divided by 2?
1.
We've got 1 here, just like we don't write sodium chloride like this. It's just understood if you write the element and that's all there's there, that you have a 1 there. Okay? So what is 2 divided by 1?
1, 2.
Okay? So then when we do this, now that adds up to 0. Okay? Now you look at the value of this. Because this side has 2 positive charges, now this side has a total of how many charges? -2. So +2 and -2, do those add up to 0? Yes. So now you know that that's the correct formula. Okay. Okay. So in the nucleus, okay, you only find protons and neutrons. The electrons are what we see floating around outside the nucleus, and that's what we're going to be dealing with here with this. It's called the slide rule, because it says on today's schedule, atomic components and the slide rule. We'll get to this in just a moment. Okay? Does everyone have this content that wants it?
One moment.
Can I lend a pencil from you? No.
Hey, you're discriminating and don't do that.
Down, how many times have I given you a pencil?
You should be.
You never told me Miss Doctor give you one. No, I didn't. To my house.
Alright, I'm good. You don't like that type?
Can you catch?
He's got one. I gave him one.
Okay. So atomic components. This is what makes up each and every element on that periodic table that you have in front of you. Okay? This isn't our living room. If it's a study hall, that's fine, but not during class. I'll say that to all students. I'll say this isn't our living room. Okay?
My pencil isn't working.
Okay. Don't associate the first letter of each component with its charge. That's pretty simple. Okay? Plus charge with protons. But if you look at negative charges, you're going to say, oh, that must be the neutrons. No, they do not have a charge. If you want to use the letter N, just say no charge. Okay?
Neutrons have no charge.
They have no charge.
Have one charge.
Each one for every one of those atomic numbers, like for cobalt, that's got 27 positive charges. Okay? So then if cobalt is neutral, which means it would not have a charge, it would have how many electrons then to add up to 0? 27. That's right. Now, these neutrons can vary. I would be led to believe that if you had learned these in elementary, you probably didn't go much bigger than 18. That's just what I think. I don't know. Because it's a really simple trap to fall into and say, oh, well, the number of protons and the number of neutrons must be the same. That does happen from time to time. And if it's neutral, these are always going to be the same for each element. It's just that these can vary. Okay? And when we say vary, carbon is probably the best example to utilize for that. Because when we talk about carbon in its natural form, it's got 6 protons, it's got 6 electrons, and it would have 6 neutrons. That is a stable form of carbon. Each one of you are utilizing that stable form of carbon right now. Do you know what that is by chance? No.
Carbon dioxide.
No.
Carbon monoxide.
You're writing with it.
Lead.
It doesn't have any lead in it.
Graphite.
It's graphite. Okay?
Sean is too smart.
So,
Is that oxygen?
no,
Who's
I,
guessing?
I'm just looking at earlobes. Okay? So, what might someone possibly have in their ear that has to deal with carbon?
Hair.
Earrings.
Hair.
More specifically, what type of earring? Diamond earrings. Okay? So, what happens is which substance is more indestructible? Graphite, which is pure carbon, or diamond, which is pure carbon?
Diamond.
You sure?
No.
Okay? If you want to cut concrete with a saw, you have to have this type of blade. Diamond-tipped saw. If you have a graphite-tipped saw, that's not going to do anything for you. But a diamond-tipped saw is going to cut through that concrete just like that old adage, a hot knife through butter. It's going to zip right through that with no problem because diamond is such a hard and sharp material. You might think, well, it's got all these jagged edges. Well, that's true. What happens is in order for that diamond to get its shape, it's either done with another diamond or a laser to do that. Okay, so carbon in its stable form has 6 protons, 6 electrons, 6 neutrons. It's when you change the number of neutrons, it becomes what we call an isotope. So, in western South Dakota, when you find, I think her name was Sue, a type of dinosaur. If you want to try to figure out how old Sue is, you use this type of carbon.
Carbon dating.
carbon dating, which is carbon 14. The carbon that we're talking about is carbon 12. But when you do carbon dating, it's carbon 14. Yes?
We named her.
Okay.
So it has a 14.
So let's see here. I think that's a good place to stop for
We asked them.
here. We're not done writing things down. Okay?
Hey! Hooray!
All right. So, what I want you to do, we'll just, since we're talking about carbon, okay? I'll use a different type of marker here. So, how many protons does carbon have?
Enough.
Okay? So, it's got 6 protons. So, what number is this? Not just the number of protons, it's got a specific name. Is it the valence number, isotope number, atomic mass? It's an atomic number. The atomic number tells you how many protons an element has. Okay? So, if this carbon is neutral, okay, it's got 6 positive charges. How many negative charges would it have?
6.
Okay? And then this is where you get the atomic mass from. Okay? On average, when you look at this periodic table, what else do you see inside that box for carbon besides C, besides carbon, besides 6?
The weight.
12.
And that is what?
12 point.
The atomic mass, which we're just going to say is 12.
What is atomic mass like measured?
Okay?
12.
What is it?
What do you suppose that is standing for? P and N. Protons and neutrons. So if we've got 6 protons, how many neutrons would that give us? You got to get N by itself.
6.
You subtract 6 from each side. There we go. Okay? But if we're doing carbon 14 dating, okay, this is how we refer to all of these particles. Okay? Here's the atomic number. Here was the atomic mass, carbon 12. Okay? But now we're going to change that up to carbon 14. We change this to 14. We change this to 14. So what do we get for N now?
8.
Oops, that's still the same.
8. And
When you subtract 6 from each side now, you get 8. Okay? So this is what we're referring to. Don't think that the protons and neutrons are always the same. Sometimes it is, but the majority of time it is not. So if we're not dealing with carbon 12, but rather carbon 14, now we've got 8 here. Okay,
so what are we writing?
So the atomic number will always show the amount of protons, right?
that's correct.
And that won't change.
That will not change.
So if you want to go higher, you have to add more neutrons.
How many is that, right?
When you say higher, are you talking about changing the element or the mass?
Just
Then the neutrons have to become more.
Yeah, just going from like
Because
12 to
these, okay, in a ratio, okay, electrons are about, for every 1,812 electrons, just the size, not the charge, but the size, you get 1 proton, it takes the mass of 1,812 electrons to equal the mass of 1 proton. What we're trying to tell you is that electrons are very, 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 very tiny. Okay? So that's why I said you need to be a little more specific. Are you changing the atomic number or the atomic mass? Okay. So go ahead and pick any other element on this periodic table and give me an atomic number. 90 what? 93. Okay, so 93. What is that element? Plutonium, right? Didn't you tell me plutonium?
No, plutonium's 94.
Okay.
I said it wrong. So
We
Neptunium.
should do number 69.
Okay, what is, maybe I should have a little clarification. I don't know, because I can't stretch this out going left and right, but I don't know if it'll be out of proportion. Does anyone have a hard time reading the atomic masses on here? Because when I look at this, when we say 93, okay, 237. See, I can read it with my glasses, but if I take these off, I don't think I could read it. But is anyone having problems reading the tiny numbers?
I can't read 110.
Okay?
Yeah, I can't
All right.
read 110 either.
So with that, every time we're identifying an element, what number is this?
Oh no. The atomic number.
The atomic number. So that means how many protons does neptunium have? 93. Okay? So the atomic mass, you can't have a partial neutron, so what we're going to say here is that 237. So the atomic mass is 237. Now, how did we get the number of neutrons for this carbon? How did we do it down here? You took 6 from the total, right?
So now we'll take 93 from 237.
That's exactly what you're going to do. Okay? So if we have 237 and we subtract 93, okay, gives us 4, 1, am I right? 144?
Yeah, and then you get Tom.
144. So, which one of those is it? Is it the electrons or the neutrons?
Neutrons.
Which one?
Neutrons.
Neutrons. So then, if this is neutral, how many electrons would it have?
93.
Because remember, these are positively charged, these are negatively charged. This just comes from subtracting these. That is true for every element on that periodic table. Okay? So if you're dealing with that of hydrogen even, atomic number of 1, an atomic mass of 1. If you take 1 from 1, you get what? 0. Hydrogen doesn't have any neutrons. Okay?
So are your protons and electrons always going to be the same?
If it's neutral, yes. So going back to, let's say, this sodium, okay? This is how you would know. And we're going to utilize that here pretty soon. Okay? So in other words, how many protons are inside the nucleus for sodium?
Tough question.
Okay?
How'd you find that out?
What one are we looking at?
Sodium.
Where's that at?
Number 11.
Number 11.
What's wrong?
Yes, it is.
Okay? So what that means then, okay?
Maybe we just spell our name.
That's how you do it. Simple as that.
Is that the slide rule? Or what is
hmm
that? So you just,
What do you mean?
Alright, so 90.
That's how you do it.
Got the same initials on me.
Tom, what are you looking at there, chump? It's the 2.
Make sense?
Not mine.
What do you mean no?
Well, you kind of just threw something on the board and said that's how we do it. You didn't.
Well, that is how you do it.
That's how you
Well,
do
where
it.
does the 2 come from?
Just pay attention.
Okay.
No, we do. What's with the lines?
All right. So we know inside this nucleus there's,
Ow, ow.
we can make this as simple or as difficult as you want.
Dallas, shut up.
We know
I'm
there
reading.
are 11
Says,
protons.
says,
Well, since we can't explain this, we'll do another element. Okay? Make it a little bigger this time. Okay?
where do you get those numbers from?
I would love to explain it, but we can't do it. Okay, let's do silver, for instance.
Why can't we do it?
Because you won't shut up.
Preston, it was you too. No, it wasn't.
There we go. That's silver. That's how you do it.
How did you figure that out, though?
That one's different from the others. That one's got
I know it does.
How did you know that?
He just remembers the Jan.
Because you add up all these numbers and every one of these, they all cancel each other out. That's why.
Makes sense. Okay, I get it.
Yeah, I'm glad. Okay, makes sense.
This is like any doctor.
How?
Said we can make this as simple or as difficult as we want. We want to make it difficult, fine. We're making it difficult. And when we get to the configurations, then it's going to be even more fun. Isn't that great? Yeah, I would love to explain this, but got too many sidebar conversations that whatever we're talking about is way more important than this. Is that correct? Okay. So if you add the numbers with that single letter, how many do you get? What's 2 plus 2 plus 6 plus 1? 11. Okay? What is 2 plus 2 plus 2 plus 6 plus 6 plus 1? 19. Okay? So when we asked, where do we get these charges from? What we see happening here is if this gets donated, which it does, okay, now this is empty. How many numbers do we see here? 10. How many numbers do we see here? 11. If these are electrons which have negative charges, and these are protons which have positive charges, okay, what is the difference between these? It's got 11 positive charges and how many negative charges? 10. So that's a net difference of plus what?
1.
And that's where that comes from, right there. Okay? The bigger these get, the more difficult it gets. And we will get down into that F block. I guarantee it. It's the manner that we get there. When we want to act like this, it just makes things a lot more difficult for those who actually want to probably learn this because they know they need it for the future. Okay.
Tall.
So what makes silver different than the others? Why does it have like an 8?
Okay.
Thomas, maybe you shouldn't sit back down.
I would highly suggest that you write this down. And when you do it, do not put it on the back of your periodic table. If you need a piece of scratch paper, we will give you a piece of scratch paper.
Is this like a note?
Okay?
Get a piece of scratch paper.
Is this something you want us to keep, Rick? That we're about, right?
Okay. So this would only pertain to ladies and gent over here that can see Bob over here. Okay? What does that say right there?
That's block.
S block. What does that say?
P block.
What does that say?
D block.
What does that say? Okay? What do you suppose these are?
S block, P block, D block, F block.
Okay? So these are not just your energy levels, but they're also your blocks. Okay? Because when you look at this, what does that say?
Good.
So then this is the first period. This one is the,
Second period.
and so on, all the way down to what number is there? 7. So these are the repeating patterns, and these are your blocks. Okay, so how many columns are in the S block?
1.
How many columns are in the S block?
2.
Okay. How many columns are in the P block?
6.
How many columns are in the D block?
7.
How many columns are in the D block? 10. And how many columns are in the F block? 14. Okay? So the S block is these two right here. Okay? S block, columns 1 and 2. Okay? P block. Okay? Helium is an exception here. Okay? That's why it's not a, that table is a little more detailed than what you have.
Why isn't it considered
Why is what?
Why isn't it considered the people?
Because when we look at P block elements, usually their outer energy level is full in column 8. That means it has to have at least 8 electrons. Okay? What's the atomic number for helium? Okay? That many. That can't hold 8 electrons. That's why on that table it's not attached, but it is on here. Like I said, that table's a little more detailed than this one. Okay? So S block has 2 columns. The P block has 6. The D block has 10. And this F block has 14. Okay? Now, a correction or something to help you out that I would prefer that you do, okay? Way out here with lutetium and lawrencium, 71 and 103. What does this say right here?
D block.
D block, just those two only. Okay? So what does it say about element 57 and 89? These are the F block. So if you start with element 57 and go all the way over to the element YB, okay, you're going to get 14. Okay? So this is part of the F block. These two are part of the D block. So if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Remember, this is part of the D block up here. Okay? Because if we put these in increasing number, that means this table would have to be really, really wide. In other words, when you factor something out, okay, like I usually use the same example. If it's a circle, okay, if you had 3x squared plus 3y squared equals 9, what do they all have in common? 3. So you can factor a 3 out of there. Oops. Equals 3. Okay? So what you're doing is you're pulling a factor of 3 out of there. So that's what we're doing here. It's kind of like pulling a factor of 3 out of here and putting it on the bottom. It just makes it more convenient to put it on a piece of paper like this. That's the only reason why. Okay. Then the last thing we'll do, okay, make your lines straight. Okay? I want you to do this now. And make sure it looks like this. Okay? All right, that's all I have. We'll catch up to you next time.